declaration, or just in the dinner today. I don't know if it's in the text, but we have for free just one non-alcoholic beverage. So if we want to drink wine or beer, we have to pay by ourselves. So take into account, don't get mad with me. And this is the border conditions for these dinners. Okay, I have to say anything. Here is the paper for writing down the groups. Yes, because today we start with the hands-on working in the first floor. Do you know where is it? In the first floor, there is a lot of tables with chairs, and we can go there and work there. So this is the idea. Yes?
If someone doesn't have a group, wants to be in a group, so they get together.
Yes, I'm alone, and we are going to help you. Okay, let's go into this last talk of the day. I will go into opinion dynamics and social influence and so on. So, okay, come on. See, yes, I connected, and it was working, but, okay. Okay. Group behavior. I'm going to speak about opinion dynamics. And all modeling opinion dynamics assume that people, when interact, they change their opinions. This is hypothesis well-grounded or just an artifact of our models? Well, this is, do you know this experiment? Have you seen it? Okay. I have a lot of videos, but I'm not going to play all of them because, fuck, okay. I'm cursing in English. Sorry. Okay. No, ha.
At that study.
The experiment you'll be taking part in today involves the perception of lengths of lines. As you can see here, I have a number of cards, and on each card there are several lines. Your task is a very simple one. You're to look at the line on the left and determine which of the three lines on the right is equal to it in length. All right, we'll proceed in this order. You'll give your answer.
Only one of the people in the group is a real subject, the fifth person with the white T-shirt. The others are confederates of the experimenter and have been told to give wrong answers on some of the trials. The experiment begins uneventfully as subjects give their judgments.
2, 2, 2, 2, 3, 3, 3, 3.
But on the third trial, something happens.
2, 2, 2, 2, 2.
The subject denies the evidence of his own eyes and yields to group influence. Ash found subjects went along with the group on 37% of the critical trials. But he found through interviews that they went along with the group for different reasons.
1.
1. They must be right. There are 4 of them and 1 of me.
1.
This subject's yielding is based on a distortion of his judgment. He genuinely believes that the group is correct.
Okay. This is the kind of things we want to model. Why people change their opinions. And we can see here, and there are many psychological experiments that take into account that we are influenced by our peers. There is another video. This is one of my favorite movies, but I don't play it today. I will play it tomorrow, because tomorrow we are going to see persuasive argument theory. So I will skip this for tomorrow. Oh, no.
All right.
No. This is a very funny video, but I don't play because I don't have time. But if we have time, we can play it in another location or out of schedule. I know what I'm going to do. Tomorrow, at 9:20, I will play this. Okay? So for those of you that are going to be here at 9:20, we are going to share this video. And 9:30, we start with the first talk, okay? So, it doesn't work here. Okay, why can people change their opinion or behavior? This is what in social science is called social influence, what in physics we call interaction. This is called in social science social influence. Social influence is, as they say here, defined as a change in individual thoughts, feelings, attitudes, or behavior that results from the interaction with others. In particular, persuasion is when this change is associated to an incorporation of information, of extra information, okay? And this is in the framework in which we are going to move. I don't know why the slide mover that doesn't work from here. I don't know. Okay. Yes, we can. So, what is the problem we want going to go through? When a group of interrelated individuals discuss about a given item or about a group of items, they are prone to change their initial opinion in order to get more like or more dissimilar to other people in the group. So these interpersonal dynamics can have two different outcomes, two different collective behavior. And we're interested in just make the connection between this mechanism linked to opinion formation, how are the collective arising states. To change this. So, why people change their opinions? There are different theories. The first theory is of social influence. No. The first theories of social influence come from sociological theories. These are 4 of them. The first one is imitation. Oh, yes, sorry. Oh, okay. The first one is imitation. It's due to Akers, a collaborator, in which in situation of high uncertainty, or when we lack of information of others, it can be rational for individuals to imitate the behaviors or the opinions of others. For instance, in a fire, or if it's some panic situation here, and something starts to run, maybe we don't know, but we start to run. That's imitation. And that's what we do when we have a little information and something is happening. We have to do a quick decision. But it's also, as we can see before, social pressure in some situations. Interaction partners may exert social pressure to conform with each other. I mean, maybe we are forced to change our opinion, our behavior, just to be comfortable in a group. Or cognition theory, what implies that we want to be like people we like to interact with. We want to be in a group when we admire or something like that, and we try to adjust our opinion, our behavior to be like that. Or just we are more in a kind of rational debate, and we interchange arguments, and we can convince someone or get convinced because we have a rational conversation, maybe in the sense that Marcelo told. There are different mechanisms for which we can influence each other, and if we want to model an opinion formation, or we want to perform an opinion formation model, we would like to know which kind of situation we would like to model, which kind of mechanism we are going to I don't know how to say in English, to use. Okay. There are also not theories. There is also empirical results, mainly from psychological experiments, that consistently have shown that people change their opinions or their behavior when they interact with others. In particular, it is known that when some people share some other attributes with other people, they're more likely to change their opinions. I mean, the more we feel close to a given person, the most likely to change our opinion. What we would like to know? Under what condition does a group reach consensus or a given opinion become predominant? Or why polarization arises, for instance? Can we predict the final collective outcome when different mechanisms compete among each other? As for instance, when some individuals tend to agree and others tend to disagree. This is the idea to perform a model of opinion formation. There are a lot of literature, a lot of models. This is a review of Claudio Castellano, Santo Fortunato, Vittorio Loreto. This is from, many of you know, it's 2009. And there is a whole chapter for opinion dynamics, and there are a lot of literature of different kind of models. Which is this problem from a physics perspective? How do interaction between social orders create order or disorder? Which is order? Order is a translation of is the way we see consensus, for instance, agreement, uniformity. And disorder stands for fragmentation or disagreement. It is reasonable to assume that without interaction, heterogeneity will predominate. So the order just comes out from interaction. The focus of statistical physics, the statistical physics approach to this problem is understand how these orders came out, okay? And the key factor is the interaction between agents, see? And how this repeats in time and how can order or disorder emerge. The first decision we have to make is how to choose, how to represent opinions, okay? Opinions, if we have a single topic of discussion, opinion will be represented by a single variable. But still, the single variable can have discrete values of continued values. And there are a whole different families of opinion models. If we want to model circumstances when several topics are in discussion, we have to represent opinion as vectors. In the class of today, I'm going to speak about discrete opinion formation model. Tomorrow, I will speak about continuous opinion model. And on Friday, I will speak about multidimensional opinion models. Okay? This is the order of the classes. So, when we speak about the classical discrete model, the number one is the Botter model. The Botter model, each agent can be in one of two states. He says it is defined by the variable that can take two values, pro or con, black and white, up and down. Initially was solving a two-dimensional grid. It followed an imitation dynamics, as the one proposed by Akers, which is the collective behavior following low information environments, as I said before. Agent has no memory, so it can assume that agents are not confident in their own opinion because are changing every time they can change. In general, starting from a disorderly initial condition, this model is evolving toward an order and order, and if the system, the size of the system is finite, it's a rich consensus, full consensus. The first works about this Water model was by Clifford and Sudbury and Hawley and Liggett, 1973 and 1975. The dynamics is very simple. We have an agent that is surrounded by his first neighbor, and this is going to pick up at random one of the neighbor, and will change, will copy the state of the neighbor. That's it. So with probability 3/4, it's going to become red, and with probability 1/4, it's going to turn to blue. Yes, that's okay? This is the model. It's very simple. If we see a snapshot of simulation, just in a two-dimensional grid or from a droplet, we can see how this system is ordering in time. So, a very useful quantity to describe the dynamics of the water model is what we call the density of active links. An active link is a link between agents we are in different states. So it's a link that is prone to change, okay? So when the system reaches consensus, there is no active links because all the nodes are in the same states. See, okay? So the system reaches consensus where the density of active links becomes 0. In d-dimensional grid, the density of active links behave in this way, okay? And it means that in the thermodynamic limit, the system converges to consensus if the dimension is less or equal to 2. And for dimension measured at 2, the opinions can coexist in the d-dimensional grids. Also, it is possible to analyze infinite system, the time to reach consensus, T sub n, and it depends, of course, of the dimension of the problem, following different scaling law with the size of the system.
Similar to Ising model?
Is similar to a Ising model with a Glauber dynamic at 0 temperature. This model has no temperature. Okay? Rho, this? Rho is a quantity that depends on time. Rho is the density of active links. One active link is like this. I have this is an active link. Can you see? Or just this? Sorry. It's a link between two agents that are in different states. I choose a bad place in the board, sorry. But this is important because the next of the class, the water model has been solved not only in grid, but also in different kinds of complex networks, as the networks that Victoria said recently. And they study how the dynamics of the water model depends when the connectivity of the network was different topologies. If you can get insight about this kind of job, you can read this paper of the group of Maxis and Miguel, that is very nice. But I will focus from now to the end of the class in this work. This work is also a paper of the group of Palma, in which they analyze the analytical solution of the water model in uncorrelated networks. And what I'm going to do now is just to follow the development of the master equation for the density of active links in this kind of system, in uncorrelated networks. Okay? So we can see if we can build the master equation for the density of active links. So,
What was an uncorrelated network?
an uncorrelated network is a network in which the connection between two nodes does not depend of other nodes. Okay? This is correct. We are going to use two magnitude to describe the evolution of the system. One is the density of active links, and the other one is the magnetization. Okay? Here, and our first step is to analyze what happened to the density of active link and the magnetization when a node of degree k, like this, perform a single flip. Yes? So we have here a node. This is neighbor with the same states. They are neighbor with the different states. We have n active links. We have k minus n inactive links. And the magnetization is the state of the node S, which could be +1 or -1, times the number of inert links. When this spin or this opinion flips, change from circle to square, what happened? The inner links become active and the active become inert. So in this configuration, we have k minus n active links, and we have n inner links. Okay? So what is the change in the density of active links? Is this quantity of active links, k minus n, minus n, k minus 2n, divided by the number of links of the networks. And the number of links of the network is mu, which is the mean degree that Vika explained, times the number of nodes divided by 2, just in order to avoid the repetition. Okay? So this is the change in the density of active links when a single spin occurs. And the change in magnetization we can calculate in the same way. See, the new magnetization minus the old magnetization divided the number of links. That's okay? So if we want to write the master equation, we would like to describe how is the evolution in time of the density of active links. This evolution in time will be given by, if we separate in the node of different degrees, by the probability we have to assume, or the probability of finding a node of degree k, times the change in the density of active links in a node of degree k. Here we are going to use that the evolution in time is discrete, and I'm going to use that the time step is 1 over n. This is going to 0 when n goes to infinity. And this d rho is the change in the density of active links when a node of degree k is chosen. And this variation in the density of active links when I choose a node degree k, it's going to be like the sum of all the cases from having from 0 to k active links, n active links, times the probability that n active links be connected to a node of degree k, to the probability of choose one of these active links, times the change in the density of active links, that is the delta rho here. Okay? Okay? So, what's the next step? The probability of having n active links among k will depend on the state of a node S. And this is going evolving in time. So it is not the same when the system is converging to the consensus, for instance. This is not going the same that in the beginning. So I would like to separate the probability of having n active link among k given the state of the node. So we introduce the conditional probability of having n active links among k given that the node is in state S, could be plus or minus 1. So we write down this probability in this way, and we rewrite this evolution for the density of active links in this way. We can follow the mathematics. And the next steps here is just to do distribution here and to write down this in terms of the momentum, the first and the second momentum of this probability distribution. Yes, this is the first momentum of the distribution B given of nk given S, and this is the second moment of the distribution. Okay? The next step is that here we are going to use the hypothesis of uncorrelated network. So we assume that the probability of having an active link depends only of the state of the two connected nodes that is independent of the other networks, as you asked me before. And it is like this: if we call P as the probability that a neighbor of a node E be in state minus S, given that E is the state of the node, it is the probability of having a node with state S connected to a node with state minus S, then this probability is binomial because it doesn't depend of the probability of the rest of the neighbor, and I can write down as a binomial distribution. If this is a binomial distribution, what is the hypothesis of uncorrelated network? I know how to calculate the first and second moment. I calculate this, and I just have to write down how is this probability. And this probability, that is the probability of connecting two nodes, a neighbor in state minus S with the center in state with S, is the number of active links connected S to minus S. This is rho times the amount of links in the networks divided the number of links connecting to another with state S. This is the density of the state S times mu per n. Okay? And this is the number of links, and this probability is rho over 2 sigma sub S. If I introduce this information here, this equation looks like this, where the first and the second moment can be written down in this way, and I have to take into account that mu, that is the mean degree, can be written as the sum of k times p sub k, and this p sub k normalizes the probability of having a node with degree k. And I do the math. I just sit down and just write down everything, and I arrive to this equation. This gives me the evolution in time for the density of active links given the density of node with the spin plus and the spin minus, that is this from here. We can check here that this equation has two stationary solutions, two fixed points. One is a rho equals 0, and the other one is a rho equal this number, which is different from 0. This is stable from mu less than or equal than 2, and this is stable for mu greater than 2. Okay? What does this mean, this solution, in terms of the Butter model? What different solution, stationary solution different from 0? Exactly. Rho equals 0, it means that the system reached consensus. Rho different from 0 means that this is a stationary solution when different opinions can coexist. Okay? We have region with opinion plus and opinion minus. This coefficient Z depends on the mean degree of the distribution. Okay? Also, we can see that this stationary solution depends on the size of the system. the greater the size, the more reduced are the fluctuation, fewer are the fluctuation, and in the limit of, in the thermodynamics limit, the fluctuation goes to 0, and this quantity remains constant, okay? This means that in the thermodynamic limit, complete order is not attained for average degree greater than 2. But in finite system, if we wait long enough, it's always appears a fluctuation that drives our system to the consensus. In finite system, we always have consensus, okay? This is how this quantity looks like, the standard solution, for different sides of the networks. This is figure 2 of this paper. So one proposal of hands-on is to reproduce this figure. You have not to do this from scratch. I'm going to share with those who are interested a collab with a Butter model running, so you can try different configuration with different networks, okay? So, I'm almost running on time, so sorry. We're going to eat later today. If we want to know how the system approach to consensus, we have to look now another quantity, in particular magnetization. So let's define, to analyze how the system reaches a consensus, let's define these quantities. We are going to call ρ++ the density of links connecting two nodes with opinion +1, and ρ-, is the density of links connecting two nodes in the states minus, okay? First, we are going to write ρ(S)S in terms of the density of links in the state S. First, we are going to calculate the number of total links from a node with opinion S. This is the fractions of nodes sigma sub S times mu per times n. The number of total links from S to minus S is the density of active links times mu per n over 2, and the total links from S to S and ρ(S)S times mu times n. And 1 is equal to 2 plus 3. So if we do this equal to the sum of these two, we arrive to this expression. And if we relate this expression with magnetization, we find the expression of magnetization in terms of the density of links in one of the states. And we can, using that, this relation between sigma, rho and sigma plus, we can write down this one. Sorry, I'm going a little bit fast, but those who are interested, we can check down the mathematics, whatever you want in the.
Actually, it's a conceptual question related to the previous one, because it seems that the solution is consensus when you have a small mean number of connections, right?
Yes.
For me, it's a little bit counterintuitive, because I would expect the opposite.
Yes, it's counterintuitive. You're right. I arrived at the same conclusion when I was looking at this problem. So I agree with you. But I don't know how to say, but we agree. We are with rho equal to 0. OK. If I write this, we can just check also the relation between, if this theoretical relation between rho and the magnetization is indeed a quadratic, I have to go? No. OK. A quadratic relation, and it was the figure 3 of the paper that also can be hands-on if someone wants to go deeper in this problem. OK? OK. So if we want to now go to the convergence of the system to the stationary state, we have to write down how is the probability of having a magnetization M and time t plus delta t. This is going to have the evolution of the probability of finding the system with a given magnetization. And this we will have the probability of going from state M plus delta K, M plus delta M, to M, plus the probability of going from M minus delta K plus to the state M, plus the probability of not changing M. This is the probability of being there times the probability of transition from going to one state to another. There is one question? Or? Okay.
How we interpret magnetization in the opinion semantics?
Magnetization is because you can reach the magnetization is because it's similar to spin. And this problem, you can have all opinions can have +1 or -1. So magnetization is all the, yes, all have one opinion. It's consensus because you have two kinds of consensus, +1 consensus or -1 consensus. Okay? And this P is the probability of having magnetization M at time t. See? We can write down the possible change in M due to the selection of a node in degree K and do a single flip spin, as we did in the first graph. And a node with spin S and degree K change its state with probability, the probability of having a node in this state times the probability of having an active link between the networks, and this can be written as rho over 2. And this produces a change in the magnetization that that came out from the first figure. So, and with this information, we can write down all the probability transitions. Okay, I'm sorry that I'm going fast and this is too much information, but all the calculation are detailed, and I have the steps that are not here, I have written down in my notebook, so we can check out in the hands-on exercises. Okay? So if we do this, we can write down the probability transitions, and we arrive to this equation. This long equation where we write down all the probability transitions. And when we do that, we go to the continuous limit, expanding P a first order in time and a second order in magnetization. And when we do that, that is this here, we just do a lot of steps, and we arrive to this equation. Sorry, you see, the rule was very simple. Just I take a spin flip, look the neighbors, copy the neighbors, and it is very simple. I can simulate in 3 lines of code. But the mathematics is not so simple. So I want to show this contrast between a simple rule and a huge mathematical development. But still, we can follow this. Okay? If we give enough time, we can do that. And we can here identify the second moment of the degree distribution, this mu2. And in the thermodynamics limit, we arrive to a kind of Fokker-Planck equation for the probability of having magnetization M. And this is which gives us the evolution of the probability of finding the system in magnetization. The solution of this, here we can go to the books. How is the solution of this problem? The solution can be written in this series of exponential. And given that, I can write down the evolution of the average density of active links just to perform this average between all the magnetizations. And if I do that, and finding the coefficient given an initial condition, this is also a whole calculation, I can arrive to this, which can be written down like this. I mean, the systems goes exponentially until towards the stationary states. So simple like that. But the exact mathematics of the probability is like this. So here is this evolution of the density of average density of active links as a function of time rescale from different situations, for different networks. This is figure 4 of this manuscript, and these are the quantities for different networks that you have seen with Victoria. So another hands-ons could be just to reproduce this figure to check out if this theoretical approximation match with the simulation, okay? I'm finishing, sorry, I'm going very quick this, but this is only the Botter model. I will say that this is a whole zoo of model of discrete. You can check out in the literature, but I will like just to came out your attention because here we fix the topology of the interaction and the dynamics was in the nodes. The nodes have dynamics. But it could happen that also the network evolves in time. And this is the coevolution dynamics, or which is a coevolving Botter networks. See? Here is very similar to the previous model, but one node here can change his opinion in 2 different ways. It can spin as before with probability 1 minus p, or can rewire. I'm not happy in this neighborhood, I change my friends. I might go to another group and go into this situation. You can read this paper, I can give it to you, but the interesting thing is that if we look at the master equation, it looks very similar to the one we wrote. So if we learn how to develop the master equation of a given problem, we have the tools to develop master equation of several models that could be interesting. This is very interesting. This is also another term of this problem. This is the nonlinear Botter model, co-evolving nonlinear Botter model, in which also it's the similar dynamics, but the probability of choosing an active link is not linear, it's nonlinear. It has a coefficient of nonlinearity. It is Q here.
The Fokker blank of this system has this term. What is the difference here? Or there is? How the Fokker blank equation changed by allowing the evolving dynamics?
Okay, so very nice question for a hands-on exercise. What I'm going to show you now is that we can map the solution of the model in this QP plane. And there are different solutions. You can have consensus, you can have coexistence of opinion, or you can have fragmentation, which looks like what is called echo chamber. So Wesley has working in characterizing echo chamber in Twitter, and there is also model about how this can be produced, and this is called via mechanism as echo chamber can produce, combining a polarization model with a rewiring process, okay? So this is a very nice paper that is recently on the archive that is why discrete model has 2 states. It can have more than 2 states, can have several states. This is a multi-state Botter model. And when you read this, you can see that if you know the equation of the Botter model, you can follow the equation of this paper. And it will be very, very nice. But the Botter model is related to data or no? Well, there is also a paper of Maxi and Miguel group when they ask if the Botter model is a model for Botters, and they analyze certain properties of the election in the United States in terms of a Botter model and the flux of P people between different counties. Okay? I'm not going to go into these details, but you can read it. And sorry for the time. That's it. We're going to lunch now. So,
Questions for Pablo?
yes. Remember, groups. And 2:30 to 45, we meet in the first floor, and we start to work all the afternoon in the hands-on. Yes?